Welcome to part 2 of 2 on our lecture covering chapter 6 from your textbook on samples and generalizations. So we had talked about non-probability samples in the previous slide. Now we're going to talk about probability sampling methods. So as I mentioned earlier, what distinguishes probability sampling is that we know in advance the likelihood of selecting each element. If I have a student population of 10,000 students and I'm going to draw 100 students from that population as a sample, then I know that every single student within that population has a 1 in 100 chance of being selected. Okay? Because you have the denominator of the fraction, you can say with some degree of certainty what the likelihood is of selecting each person, what chance each person had of ending up in the sample itself. These methods always use some sort of random selection. I want to emphasize here that the word random has kind of been connotated in different ways, especially recently. People describe things as quote unquote so random, meaning that they're just kind of chaotic. It's not random in terms of technique. It is random meaning that every individual has the same given likelihood of being selected. This is not the same thing as haphazardly, randomly selecting elements. The random aspect means that everyone has an equal chance of being randomly selected to be in the sample. The size of the sample and the homogeneity or the sameness of the population on a certain characteristic affects the degree of error as a result of chance. So the larger the sample is, the more confidence we have that the sample is representative. Now let's stop and think about that logically for a minute. Again, let's use the example, if I have 10,000 students and I have the resources and the time to enroll 5,000 of them in my study, right? Larger sample on the one hand. And then if I was only able to draw a sample of 100, with the sample of 5,000, I have more confidence that the sample I drew is representative just by virtue of I'm looking at more people within the overall population. The smaller the sample gets, the less confident we have that it's representative. So this is going to go back to a theme that's going to run throughout the class, which is that bigger is better when it comes to a sample for any research study. There is a diminishing returns that you run into eventually, and there are certainly always limitations of time, money, and resources. But the bigger, the better is always a good rule of thumb when it comes to drawing a sample from a population. The more homogeneous the population is, the limited amount of variability on whatever characteristic it is you're interested in, you can also have more confidence in how representative the sample is of any particular size because there's just less variability. So they're not that different from one another on this particular sample. If you're interested in how something about socioeconomic status relates to a certain psychological characteristic, and you're drawing from a very homogeneous group of people that are all at the low end or the high end or the middle of the socioeconomic status, then you know that you can make certain assumptions about your sample being representative on that variable because there's not a lot of variability in the population you're looking at. Of course, keep in mind, now you've just limited the generalizability of the findings, right? Now you can only generalize back to that narrow band of socioeconomic status. So there's a payoff here, there's a back and forth. But ultimately, if the sample is homogeneous, if there's not a lot of variability on the characteristics that you're interested in, you can also feel pretty comfortable in representation even with a smaller sample. The fraction of the total population that a sample contains does not affect the sample's representative unless that fraction is very, very large. So, it only gets into situations where I'm going to look at half of everybody that it really makes a strong argument for representation. But the larger the portion of the sample that you get of the overall population, the better. The quality of the sample is really answered by two questions. First of all, clearly defining the population. Are you being specific as you can be about the population from which you're going to draw your sample? And then what method did you use, right? This is how we often talk about the quality of a sample. So first and foremost, as I mentioned earlier, you have to define the population clearly. You have to say specifically from what population are you going to select cases, and then to answer question 2, what method did you use to select cases from the population? How did you go about it? So by defining the population clearly and then allowing some rationale That allows for some rationale and some confidence about how those results can be generalized. And then you also start to address the issue of whether or not you can generalize across other populations, right? Let's say I'm studying college students. If I know exactly details about that population of college students at Virginia Tech, for example, then I can start to think about how generalizable it is to all college students, or all college students in the United States, or all college students in state universities, whatever it is I'm interested in. Clearly defining the population is the first step in that. And then I have to define my sample components. And as you remember, the idea is you want a representative sample because that's going to allow you to generalize back to the larger population. The sample represents the selected population. And there are two possible problems that come into play here. First of all is that your sampling frame, remember that's your list of every element within the population, is incomplete. If I go to the registrar and get a list of every Virginia Tech student and they've left off a lot of students for one reason or another, that's going to affect my ability to get a generalizable sample if it's just an incomplete frame. And also the other problem, and this is the one that's more practical that you see more frequently, is failing to obtain an adequate response rate. So even if I have a really great complete sampling frame, but many sample members, I can't reach them, they refuse to participate, whatever it is, then that can potentially yield systematic bias into my sample. So this concept of non-response, of getting someone who doesn't respond, who chooses or opts out of participating, or who can't be reached, it is a major hazard, especially in survey research, because non-respondents are likely to differ from those that do take the time to participate, and they are likely to differ systematically in important ways. So if each element has a predetermined likelihood of being selected and you get a good high response rate, then hopefully you're not introducing any systematic bias. But this is rarely the case. There's almost always a problem with non-respondents or people that choose not to participate. And you have to try and look and you sort of do a post-mortem after the fact of how are non-respondents potentially different than those that chose to participate. And if they are different in some way that I can identify, at least I can talk about that and how that limits my generalizability when the study is done. So there are four common probability sampling methods. We've already talked about non-probability methods, things like convenience sampling or haphazard sampling and quota sampling. Now we're going to talk about these four types of probability sampling methods, and they are simple random sampling, systematic random sampling, stratified random sampling, and cluster random sampling. I get my fingers in the frame there. We're going to talk about each of these in a little bit of detail on the next two slides. So the first is simple random sampling, and it is pretty much contained within the name. You develop a procedure that generates numbers or identifies cases on the basis of chance alone. This can be done in a lot of different ways. It can be done with a coin flip or a dice roll. So you basically, let's say that I have a list of all the students in the university. Theoretically, I could sit there and I could flip a coin for every single one. I could roll a die. 1 through 3 means this person is going to be sampled. 4 through 6 means they're not. That's pretty tedious, as you can imagine. Utilizing a random number generator or a random number table that's already been generated. This is a way we often go about doing this a little easier. There's plenty of programs where you can put in your sampling frame. You can put in like a list of every Virginia Tech student and have it randomly select you 100 or 1,000 or 1,500 people, whatever it is, whatever the size of your sample is going to be. Back in the day of everybody having a landline, which is of course an old-fashioned concept, but back when everybody had a landline, we used to do, this is before my time even, there was a process called random number dialing, random digit dialing, where you would connect to a phone. It would literally just randomly select a series of numbers within a certain phone prefix, within prefixes for the region you're in. Corresponding to the area where you were doing the survey. So it would just sort of, through that random number generation, it would just randomly select phone numbers. Now, of course, this doesn't work very well in the era of cell phones. But the probability of selection in a true simple random sample is equal for each element. So think about that for a moment. Every unit within the larger population has an equal chance of being randomly selected. That is the sort of basic definition of a simple random sample. However, that might sound ideal, right? But there are times when we need to be a little more systematic in a variety of ways. When it makes sense logically, it makes sense practically, and it's much more advised to do it in another way rather than just pure random sampling. The first one is called systematic random sampling, and this is a variation on simple random sampling in which the first element is selected randomly from a list, and then every nth or every other, every 10th, every 100th, every 50th, whatever it is, that nth is to represent a number, every nth element is selected. And so you say, okay, I have a list of every Virginia Tech student. There's 35 odd thousand students. I'm going to randomly select one. Let's say it happens to be number 13. And then for every 150 more students, so 163, I'm not going to do the math on that, 213, so on and so forth, whatever it is, whatever it is. I'm going to go ahead, I'm just every 10th person, for example. So I might start with number 3, and then I'm going to select 13, 23, 33, 43, 53. It's just a method of randomly selecting in a systematic way. There is a potential problem associated with this technique, and it's called periodicity. There might be some existing regular periodic pattern within your sampling frame that is introducing some systematic error. There's an example from your book is that houses in a development might be like a pre-planned development of a neighborhood might have 8 houses on every block. If you happen to select every 8th house, what you're going to end up with is the same house on each block, right? So that might be all the houses that face the main street on one side, for example, right? And there might be something unique about those houses. Maybe they're corner lots, maybe they're larger, therefore they're more expensive, therefore the people that buy them might have a slightly higher socioeconomic status or wealth compared to the other people in the neighborhood. This is just an example, but there's plenty of ways in which there is there's some error already existing in the frame. There's some periodic thing that happens, and you might accidentally tap into that in a way that introduces systematic bias. If you look at illustration 6.4, exhibit 6.4 in your book, it explains this. I know this is a very busy slide, so I'll take my time with this. These are the other 2 types of probability sampling methods. The first is stratified random sampling. This is where you know something about the population, about the whole sampling frame to begin with. You're aware of certain characteristics about all the elements within that population. For example, if I have gender information, if I have socioeconomic status information, if I have some kind of characteristic that I already know about everybody within that population, then I can distinguish every single element based upon that characteristic. And I can create what are called strata. I can break the larger population into groups, into strata, and then I randomly select from each of those strata. If I want to have an equal number of males and females, again, I know I come back to this, but it's just one of those things that always works for an example. If I know that I want to end up with equal numbers identifying as either male or female in my eventual sample, and I know the gender identification of my population, I can split it into 2 separate lists, one of which is males, one of which is females identifying, and then I can randomly select from those 2 parallel strata so that I end up with a sample that's 50% male, 50% female. Okay, that's what stratified random sampling is. You're taking a step to end up with a representative sample in most cases. In most cases, what you're looking for is something called proportionate. And that means that you want whatever that characteristic is, you want your sample to reflect the larger population. So, for example, with race and ethnicity, if there is 20% of racial group A in my population of interest, then I want my sample in a proportionate technique, in a proportionate approach. I want my sample to have 20% of group A, whatever that race is, Caucasian, African American, whatever it is, right? Sometimes what you actually want is a disproportionate sample. You still have that information about the population. You still know how they fall on a certain characteristic. But when you want the distribution of your sample to not match the population, there's an example from your book. Eisenberg's research in 2007 was a mental health survey study at a university. This is called, it's looking at the mental health of graduate and professional students. And they selected a higher fraction of graduate students than undergraduate because they wanted to compare graduate to undergraduate, but there's significantly less graduate students. So if I went out and did a proportionate sample, let's say that 10% of the students at Virginia Tech are graduate students and 90% are undergrads. What I'm going to end up with is uneven numbers. If I do a proportionate stratified sample, I'm going to end up with, let's say I pull 100 people. I would end up with 90 undergraduates and 10 graduate students, presumably. Okay. But that really precludes me from being able to run lots of different statistical analyses that require equal groups. If I want 50% grad students and 50% undergrads, then I can disproportionately sample based upon that information that I have. I can create those two strata of graduate and undergraduate, but I can draw 50% of my sample from here and 50% from here. So it really depends on your design and what it is you're studying as to whether or not you want a proportionate or disproportionate sample. Another type of probability sampling method is called cluster sampling. This is useful when you don't have a sample frame. For example, when you're looking at all Americans, right? I don't have a list of every American in the United States. So when my population is spread out over a large area, or when it's a really large population and it's difficult, there are naturally occurring clusters, elements of the population. And each element exists within only one cluster. Okay. There's lots of ways we can think about clusters. Schools, blocks, counties, states, east of the Mississippi, west of the Mississippi. Like these are clusters that are created. You live on one or the other, right? Unless you're, constantly on a riverboat in the middle of the river, right? Ultimately, you're in one of the clusters. So I'm just breaking things down into clusters that are useful for me. Let's say that I'm interested in all elementary school students in Virginia. Okay. I don't have a list of every student who's in elementary schools in Virginia. That's not accessible to me, for example, or I can't get that information for one reason or another. What I can do, though, is I can say, well, there are this many counties within Virginia. I can randomly select. Sometimes there's a two-stage procedure, multiple stage procedure. I can randomly select from a list of every county in Virginia or school district. Let's do school district. Every school district. I could then randomly select 10 school districts. And then it's much, much easier to go in and maybe get a frame of all of the students in that particular school district. And I could randomly select from that list. Okay. So I have to identify the clusters, randomly select a cluster, and then within that smaller unit that's much more manageable, I can randomly select my sample from that smaller cluster. Like I said, you can do clusters within clusters within clusters, multi-stage. I could start off and say, okay, there's 50 states in the United States. At the moment, at least, we'll see about DC and Puerto Rico soon enough. But of those 50 states, I'm going to randomly select 5. And I end up with Virginia, Nebraska, Utah, California, New York, and Connecticut, whatever, right? Then within those states, I can say, well, within Virginia, there's 150 school districts. I'm going to randomly select 10 school districts. I'm going to randomly select 10 school districts from Utah. I'm going to randomly select 10 school districts from Alaska, from New York, from Connecticut. Now I've got these much more manageable clusters, and I might go in and then have a full list of all the students in each of those school districts and randomly select students to participate in my study. The more clusters are used in a sample generally, the more it is representative of the overall population. But this increases the cost of data collection. The more you cluster, the more stages you go through, it can get a little more expensive and more difficult. Here's an example of stratified random sampling. If I have this community X that has 10,000 people in it, I can get sort of maybe from the census or whatever, I can get a racial breakdown of that community. Okay, so in this case, my community is 70% white, 15% Black or African American, 10% Latino or Hispanic, and 5% Asian. Okay, if I want a proportionate sample, then we're really talking about this one on the left here. As you can see from the pie graph here, my sample, 1 from 20 in each stratum in this case, stratus plural, 1 from each stratum. What I end up with is a pie chart that looks very much like my larger population, right? My sample reflects my population in a proportionate manner on this characteristic. But if I want to end up with 125 people in each group so that I'm studying ethnicity or race, for example, or how it affects certain things, then I might want to choose a disproportionate sample where I end up with 125 people in each. There's equal representation. It looks nothing like my overall population here, and there are reasons why you might do either of these depending on what it is you're studying and what the theory is that's driving your particular study. Here's an example of multi-stage cluster sampling. I kind of alluded to this already. I randomly select states from the United States. That's my first cluster. I randomly select cities, towns, and counties within those states. And then I randomly select schools from within those cities and towns. And then I randomly select students within each school using a simple random method, right? I might use a random number generator. So once we have a sample, there are lots of ways in which we can examine it and figure out, at least to some degree, how much error. Did I do a good job? Did I get a representative sample or not? To deal with potential sampling error, we often will then take a look at the properties of the sampling, how they're distributed, how those properties are distributed. And there's plenty of statistical calculations that we can use to estimate sampling error. Things like the arithmetic mean is a simple example of that. If I know what the average socioeconomic status or family income is for my population, then I can just go look at my sample and calculate their average income. If it's close to the mean of the population, then I know that it's pretty representative, at least on that characteristic, right? If it's not, then just through simple sampling error, I might have ended up with a sample that happens to be significantly wealthier or significantly less wealthy than what I'm really trying to look at. So that might be a large amount of sample error. And now sometimes it's more complicated than that. That's an example of where it's just simply looking at the mean. Sometimes you don't know the mean, right? So it can be a problem. But there's a number of techniques we can use. Either way, regardless of what method you use, there's always some error in your sampling. As I mentioned, the lower response rate, the less people that choose to participate who opt not to participate or you can't get a hold of, the higher the probability that the sample is not representative and therefore is less generalizable. It's increasingly difficult to obtain a high response rate for large-scale surveys for a variety of reasons. As I mentioned, very few people have landlines. Most people use cell phones. Caller ID allows us to screen out unknown callers. So if I'm calling you from the university and you don't represent, from my office trying to conduct a research survey and you don't recognize the number, it's not your friend or family, then you may not pick it up. Also, we've kind of changed as a culture through telemarketing and just things have evolved where we feel much more comfortable just saying no to telemarketers. And, we might confuse a telemarketer with a researcher. No, thank you, I'm not interested, hang up. That's now a non-respondent. And in a sense, that's an introduction of sample error. There's also a general cynicism and distrust of government that has undermined trust in the value of social research. So people are just less willing to participate because they don't see the value of it as much as they might have in the past. So it's a problem that we have to deal with, is sampling error, because this is where we're starting from, right? Before we've even conducted our study, if you can design a perfect, rigorous, extremely empirical study, and you can conduct it with tons of attention to detail and tons of regimented structure. If your sample's not representative, your findings don't really mean a lot when it comes to the larger population. All it tells you about is the people that you studied. It doesn't tell you much at all about the overall population that you want to generalize to. So there are, as I mentioned, many techniques that we can use to estimate how much error there is in our sample. These generally fall under the heading of inferential statistics. It's a mathematical tool for calculating sample error. So we know that the sample that we get is just one of many that could have been drawn from the population. Okay. That's the ones we happen to get randomly. That's who we ended up with. But on any given day, we could have pushed start on that random number generator. It's random. It could have spit out entirely different numbers, and therefore we would have ended up with a very different sample. There's something called a sampling distribution, and you can look at an example in your book. That's a plot of the means of all the possible samples that could have been drawn. What it does is it kind of says, okay, there's 1,000 people in your overall population. You're only going to study 10. Well, how many possible? Well, there's 100 possible combinations therein, right, that we could have ended up with. It looks at all those possible samples you could have gotten based on some characteristic, and it shows you how much error there is in your particular sample. So many of these distributions are quote unquote normal distributions, right? They are represented by the bell curve, as we've already discussed. This normal distribution is symmetrical and it's in the shape of a bell. The most frequent value of the sample statistic, whatever it is we're interested in, the mean, is identical to what's called the corresponding population parameter, the actual mean within the population. And we can look and say, okay, our sample has this mean, and we know the mean within the larger population, what's called the population parameter. The real mean of the whole population is this. It's the true value. Let's compare those two and see if our sample falls along the mean or not. The value of a statistic, such as a mean that's computed for just our sample, is called a sample statistic. As I said, the population parameter is the actual mean of the overall population. And if you have that information, it's great. Sometimes you have to estimate it, though, because you don't have it. If you can measure the entire population, if you're able to do that, or you have that data from some previous thing like a census, then you can calculate the actual mean, and it's the parameter of the population, right? Otherwise, we have to estimate it. A predictable proportion of cases are going to fall within a certain range on the normal distribution. So we can estimate whether or not our particular sample is a good representative one based on that. So this is the bell curve, which you're going to become, obviously very familiar with over time. We know that that 95% of our population is going to fall within 2 standard deviations of the mean on either side, right? So the majority of people fall within this section of the bell curve. Only 2.5% fall out over here, and 2.5% fall out over here. In this situation, let's say that I'm working with a population where I know that the mean family income in that population is $64,507. Okay, that's right here in the middle. It's a normally distributed. Now, as we know in the United States these days, with wealth disparity, it's not actually a normal distribution, but for the sake of argument, let's stick with it, right? There's a huge tail over here on the United States wealth distribution, right? It's not a normal distribution. But putting that aside for a moment, if I know that in this particular county, for example, it does follow a normal distribution and the mean is 64,507, and then I pull my sample, I want to see where my sample's mean is. So I take the 100 people, for example, that I'm studying, and I ask them, what's your mean family income? How much what's your family income? And then I calculate the mean of those 100 people. I can figure out where my sample falls. And what this distribution shows me is of all of the possible samples I could have drawn, the majority of them are going to fall in here. But if I end up with one that is over here on the tail in the upper or lower range, then it's probably not a representative sample. There was a lot of error in my sample, and I might want to reconsider drawing another sample. As I mentioned, when it comes to psychological research, bigger is generally better. Okay, but there are always limitations, and there is what's called the law of diminishing returns. It may be that if you're looking at a population of 100,000 people, that you can get away with only studying 100. And if you can, that's great. But if you can study 1,000, that's better. In most cases, that's better. But you have to look at the difference in cost of time, energy, money, and resources between 100 versus 1,000. And you have to figure out if that difference is worth the increased generalizability, if it's worth a more representative sample. And it's not always yes or no. There's some gray areas there that have to be determined based on a lot of parameters. So to determine how big a sample size you need, right? So if you say, I want to study all college students, how many people do I need in my study to feel comfortable that it's representative? So you need to know a few things. You need to know the degree of confidence that's desired, okay? And that gets to an idea of statistical testing. Do I want to have, in most cases, we usually use the term, I want to have P less than 0.05, meaning that I want to have 95% confidence in my results. We won't get into that in great detail in this chapter, but the idea being, how confident do you want to be? Again, more confident is always better than less confident, but there are limits. You need to know the homogeneity of the population on that particular characteristic. If you're interested in something that's related to income and you're studying a population that has a very narrow band of income versus a wider distribution, you can draw a smaller sample and still feel pretty comfortable. If there's a lot of variability within your population, a larger sample is something that you need to consider. You need to know the complexity of the analysis that's planned. Okay, and this is a little bit in the weeds for us in terms of the amount of discussion we're going to have about statistics. But as a rule, simply, the more tests you're going to run, the more likely it is that you're going to have a positive result in error, right? That you're going to have a false positive, so to speak. The more tests you're going to run, generally speaking, the larger sample you need to have confidence in your results. So the complexity of the analysis is important. If you're planning to just run one simple statistical test, a smaller sample may be okay. If you're going to run multiple complex analyses, then you want a larger sample. And then lastly, the expected strength of the relationship to be measured. If what you're studying based upon past research, based upon theory, says that this is a really robust, powerful relationship between your independent variable and your dependent variable, for example, then you may need a smaller sample. If it's a very small, if it's a real relationship, but it's kind of weak, you need a larger sample in order to be able to detect it. So this is another factor you have to consider in how big of a sample you want. There is a technique that we use to give you a precise estimate of sample size required, and it's called statistical power analysis, and we're going to talk about it on the next slide. So, statistical power analysis is a statistical analysis that you run, that you say, I'm studying this hypothesized relationship in this population. You feed it a fair amount of information about certain characteristics, and then it spits out a number telling you that in order to have statistical power, in order to have the ability to detect the difference that you're looking for in this population, if you're right in terms of your hypothesized relationship, you need this many people. It'll give you a number, and then you decide, am I going to shoot for more than that number? Am I going to be satisfied with less than that number for some theoretical reason? But it gives you a rough estimate. There are some very general rough guides that social scientists usually operate from. If you want to do a simple analysis on a national population, for example, if you're going to run one simple or two simple tests, generally speaking, an N, the letter N, the italicized N, is a symbol in research that means the number of people within your study, number of people within a sample, within a group. So if you see large capital N, or sometimes lowercase n is referring just to a group within the sample, it is the number of people in the study, the size of the sample, number of elements, excuse me, within the sample. Generally speaking, if it's a simple analysis plan on a national scale, a national population, you generally need about 1,000 to 1,500 people. If you're going to do some detailed analysis on a national population, you generally need about 2,500 people. If you're going to do a local or regional population, and then maybe you can get away with 100. But of course, this puts a limit on how generalizable it is, right? Because now you're only dealing with a small regional or local population. So these are very, very rough estimates that social scientists usually start with. But if you do a statistical power analysis, you utilize what's called a contingency table. And this shows how the responses to one question on the dependent variable are distributed within the responses to another question, the independent variable. If you know this in advance about the population from past research, this tells you how big a sample you need to utilize in order to be sure that what you observe is not just due by chance alone, to have statistical significance. There's a test called a chi-square that allows you to determine the likelihood of a relationship that is due to chance alone. It's an inferential statistic, and it tests the hypothesis about the relationship between variables in this contingency table. And when we're fairly confident that the relationship did not happen by chance alone, we use the term statistically significant. What this means is that we have a certain degree of confidence that what we're observing is not due to chance. We didn't just get a bad sample that happened to just by random chance have that relationship. We have some degree of certainty that it's actually due to the hypothesized relationship between the variables. Typically, we utilize what's called a p-value of 0.05 or less. Lowercase italicized p is the symbol for this statistical significance, this related to a test that we run. And basically, various inferential statistics will spit out this value that says p less than 0.05 means that there's a 5% chance or less that the result that you got was entirely due to chance and not to the reasons why you hypothesized it was going to happen. So sampling is an incredibly powerful tool. It allows us to practically, realistically conduct relatively small scale studies on a relatively small group of people that can then be generalized to a much larger population. It allows us to study theories that explain, for example, all human behavior in a practical way that can actually get done, on a relatively small sample. We can be confident that our results are generalizable if we utilize these good probability sampling and analysis methods. So the laws of probability and chance help us to select a representative sample from the larger population that makes the actual study itself manageable. It makes the analysis, practical, whereas it would be improbable or impossible to do it on the entire population. So it's an incredibly powerful tool to be able to make assumptions about the larger population as a whole. Careful selection, controlling for bias, rigorous statistical calculations, and diligent replication of the study over and over with different populations only serves to increase the generalizability, the external validity, and it increases our confidence in the findings that can then be applied to all subjects and scenarios within a larger population. So it's an incredibly important and powerful tool in the scientific method.